Good afternoon. So today we cover section 5.2, definite integral. So we'll start from a very important definition. We'll define a definite integral. And let's assume that we have a function f defined on an interval a, b. Okay. Then we take this interval and form a partition. That is, we assign points x1, x2, x3, and so on, where x0 coincides with A and xn coincides with B. Okay. Then, so make a partition x0, x1, xn. Then we pick sample points. Pick sampling points. Which we call x1 star, x2 star, xn star. Basically, inside each subinterval, we pick a point. This I call x1 star, x2 star, and so on. Remember, these points, they could be either the leftmost point of the subinterval, the rightmost point of the subinterval, or somewhere in between. Okay. Then we say that define an integral from a to b f of x dx to be equal to the limit as n goes to infinity of the following sum. I goes from 1 to n f of x phi star delta x. So here, delta x, normally if they're equal lengths, it's b minus a over n. That's the length of individual intervals. Okay. So this definition is valid if the limit exists and is the same for all choices of sampling points. So for instance, it could happen that if I choose the sampling points to be the left side of each interval, the left-hand rule, and I take the limit, I get a number, then I choose them to be the right side of each interval, and the limit is different, then this definition doesn't make sense. So it only makes sense if the limit exists and if it's the same for any choice of those sampling points. So I'm going to start by making an introduction. So let's look at this new symbol and talk about its components. First of all, this guy here is the integral sign. And it looks like an elongated S. Why S? Because it's equal to a sum. So it's a limit of a sum. So the symbol S comes from that word. Okay. A and B are the limits of integration. Limits of integration. This here, F, is called the integrand. And finally, this differential here tells me what is my independent variable. Okay, my horizontal axis is called x in this case, and this variable has to match, the variable upon which the function f depends. We call this variable the silent variable of integration. So let me show you. So the limit of from a to b, f of x dx actually can be written as the integral of f of y dy. Or I could insert any letter, and the answer won't change. Why is that? Well, if you look at the right-hand side of this definition, okay, and if you take f to be x squared, remember we actually did this exercise last time. We said let's consider the parabola, okay, f equals x squared, and we actually calculated the sum. What was it equal to? 1/3, right? So we got a number, 1/3. Does this number depend on x? No, it's a number. It's not a function. So whatever you get as an answer here does not depend on x. So x cannot appear in the final answer, so you can replace it by anything else. The answer won't change. So we call it a silent variable of integration. So x or y or anything else at all. Questions? Question?
Yeah, I'm a little bit confused. Most of the time we plug in x as the independent variable and not y. So in the case of the right-hand side, are we plugging in a y value of a and then y value of b?
Y is just a variable. I can call it alpha.
Okay,
I can
so
call
like
it
t, for instance.
t.
Okay.
Absolutely. Yes. So you're right. The convention is that usually when you draw a graph, this is y, this is x. So not to get confused, we don't often use y there, but we can. Yeah. Okay. So finally, this guy here also has a name. This is called the Riemann sum. And we'll practice to evaluate such sums today. Okay. So what is the meaning of this new object? Let me do it here. So if the function of x is non-negative on the interval a, b, then the integral of f of x dx, what is the meaning of that? Do you remember?
Area under
Exactly, because we already saw this right-hand side. We only did it for non-negative functions, and we said that's the area. Remember, we split it into a number of vertical rectangles. We calculated the area. So this is the area under the curve f of x between a and b. So it has a very clear meaning for non-negative f. Okay, now what happens if f changes sign? So for instance, we can consider this kind of function. See, this takes both positive and negative values. So if you look at the definition, you can see that when you do the Riemann sum, we can do these. So first we have these rectangles, and we have these rectangles. Okay. And if you look at the formula, they all have the same base. They all have different height, and the height of these is actually negative. So we can do them separately. We can group these together, and we get the area under this part of the curve. And then this here gives me also an area, but it has a negative sign, because each of the components here has a negative height. So if we call this area A1 and this area A2, then the integral of f of x dx is equal to A1 minus A2. This is called the net area, or the signed area. Net area, or signed area. So normally we will assume that the function f that appears under the integral is either continuous or it has a finite number of discontinuities. Okay. And next, I'm going to show you an example of using this definition to calculate the integral. And this example is such that we will know the answer before we did any calculations. Okay. So in this example, we set f of x is x minus 3. We'll say that x belongs to the interval from 1 to 4. Evaluate f of x dx by using the definition. Before I use the definition, I'm going to give you an answer. So this function is a straight line. And this is what allows me to give you an answer, or you're going to give me an answer. Okay? So let's plot f of x, which is x minus 3, as a function of x. At 0, we get minus 3. It crosses the horizontal axis at 3. Okay. Its value at 4 is equal to 1. Its value at 1 is given by 2. So we're interested in the integral of this function between 1 and 4. Okay. So we talked about that. It actually does change sign. So to calculate it simply, we can calculate this area, and we can calculate this area. And then remember that this area comes with a negative sign, right? So let's call this A1, the positive area. Let's call this A2. And let's calculate them from geometric considerations. This is easier. What's the area of this object? It's a triangle. 1/2. It has a base of 1, the height of 1. So it's 1 by 1 over 2 is 1/2. This one, what's the area of this? So 2. So this is 2 times 2 over 2 is 2. So what's the answer? We have A1 minus A2 is 1/2 minus 2 is minus 3/2. So whatever magic we're doing here, we're expecting to get this answer. Right? So let's keep that in mind. And perform the calculations. We're going to use this definition. Okay? In order to use the definitions, I have to know delta x, I star, and f of that amount. So let's do it step by step. The easiest one is delta x. We have to go b minus a over n. So it's 4 minus 1 over n is 3 over n. Questions? Okay. Now we have to create a partition. So A is 1, B is 4. What is x1? So I'm going to have x1, x2, x3, and so on. So each of these intervals have length 3 over n, right? 3 over n. 3 over n. So what is the value of x1? It's to the right of 1, the distance is 3 over n, so it's 1 plus 3 over n, right? Now, what's the value of x2? It's 1 plus twice that thing, so 2 times 3 over n. This guy is 1 plus 3 times 3 over n. So we can see the pattern. The pattern is that xi equals 1 plus, so for each I have to step I times. So I have I times delta x, 3 over n. Questions? So these are the values of x1, x2, x3. These are not quite what I need. I need sampling points, and this is really my choice. I'm going to use the right-hand rule. Use the right-hand rule. What does it mean? That if I have an interval xi minus 1, xi, I'm going to take my sampling point to coincide with the rightmost border of that interval. So xi star is going to be equal to xi, which is 1 plus I 3 over n. The last step, before I can write down the definition, is to evaluate the function at this point, f of xi star. So I go here, f of xi star. What's my function? It's x minus 3. So I have to take the argument minus 3. And that's equal to 1 plus 3i over n minus 3. And that's equal to 3i over n minus 2. Okay, so I evaluated my function at all the sampling points. And now I'm ready to use the definition. Please ask me questions at any time. So we write down from 1 to 4, x minus 3 dx. This is the integral we're trying to evaluate. This is the limit, as n goes to infinity, of the Riemann sum. And under the sum, I have f of xi star. That's the expression I got, 3i over n minus 2 times delta x. That's 3 over n. So again, this is f of xi star, and this is delta x. So now I have concrete numbers and the formulas, and I have to evaluate first the sum and then the limit. Okay. So I continue to write limit. So to evaluate the sum, I notice that this is a constant. It doesn't depend on I. So this guy can actually come out here. So I have 3 over n. And here I have a sum of 3i over n minus 2. Okay. The next step, I'm going to split this into two sums. I'm going to have a sum of 3i over n minus, like this. Next, I notice that in this sum, I have I times a constant, 3 over n. So this constant. This constant can come out. So I have 3 over n, the sum of I, And this I can rewrite as 2, the sum of ones. Questions? So I simplified it as much as I could. And now I have 2 sums. Okay. And both of them we can evaluate. The first sum, so let's do it here. What does this stand for? This stands for 1 plus 2 plus 3 plus 4, and so on, all the way to n. That's called an arithmetic progression. And we have a formula for it, right? You don't have to remember this formula, but you must have seen it before in some class or another. Okay, and this one, I want you to tell me what this is equal to. So either 1 or n. So what do we do here? This is a machine. We have to take this and add it for each I. I goes from 1 to n. So we're going to add this thing together n times. So we go 1 plus 1 plus 1 plus 1 plus 1 n times. So this is n. Questions? So I evaluated both of these objects. So this is n plus 1 over 2. This is n. So I continue here. Limit as n goes to infinity. I have to collect everything I have here. So 3 over n, 3 over n, n plus 1 over 2 minus 2n. Okay. So something is going to simplify. I'm going to divide through by n. One second. So 3, this n cancels, and I'm dividing by n. So I have 1 plus 1 over n over 2 minus 2. Okay, dividing through by n, all the terms. And now I can take the limit. I do this in order to take the limit. Now the limit is easy, because 1 over n goes to 0 as n becomes large. So this is 0. So I have 3 times 3 halves minus 2. So this is the answer I get. And we'll go here. See? It's the same thing. So you can see 2 methods, right? This is done very quickly. This is long and painful. But we could only do this because these were triangles, right? This new definition eventually will give us a tool to evaluate the area under curves, not just straight lines. Question?
I'm sorry. How did you divide everything by n again?
So here, let's write this. I have 3. This n cancels. So I have 3. And I divide by n. Here, n plus 1 over n 2, right? And I divide by n here. And from here, I get this.
Oh, okay. All right. Thank you.
More questions? Okay. Very good. So it is actually very rare when we can complete this calculation and get the exact numerical answer. Again, this was possible because it's such a simple function. So sometimes it makes sense to approximate. Let's not calculate this, the limit, but we can get an approximate answer. Okay. So in order to do this, we introduce the midpoint rule. So simply put, this rule allows me to approximate this integral by a finite sum of f of xi bar delta x, delta x. What's xi bar? So let's draw one of the intervals from xi minus 1 to xi. Remember, right point rule, we take our sampling point here. Left point rule, we take it here. Midpoint rule, we use the middle. So we say that xi star simply equals xi bar, where it's the middle point. Xi bar, xi. Okay. Is it me? No. Okay. Fine. So this is the midpoint, and that's the name. Was there a question? Okay. What's that music, right? So this is the midpoint. And let me give you an example of how we can apply this rule to approximate a particular integral. So approximate the integral from 0 to 1 x squared dx with n equals 4 by using the midpoint rule. So let's draw. Every time they ask you to evaluate the Riemann sum, the best thing to do is to draw your interval. Actually, write down the partition. Find the sampling points. Do it systematically, and then it's very easy. So we go from 0 to 1. They specify n equals 4. So this means that we divide it into 4 subintervals. This is 1/2, 1/4, 3/4. 4 intervals. Now we have to find the sampling point, which has to be the middle point, because we're using the midpoint rule. So this one here, x1 bar, what is it equal to? 1/8. Okay. x2 bar is 3/8. x3 bar 5/8, and x4 bar is 7/8. Questions? So we know our points. Just put it here. We have to evaluate the function at these 4 points. And the function is x squared. So f of x is x squared. So f of xi is just xi squared. So we can say that the integral from 0 to 1 x squared dx is approximately equal to, okay? Each term here will contain the multiplier delta x. So I'm going to take it out of the bracket. And I forgot to calculate delta x. So what's delta x here? What's the distance between my points in the partition? 1/4, right? N equals 4. The total interval is 1. So it's 1/4. So I have 1/4 that comes out. And here I have the sum f1, f x1, x2, x3, x4. So 1/4 of 1/8 squared, 3/8 squared, 5/8 squared, 7/8 squared. Okay. So if you put it in your calculators, maybe one of you can do it here, if you have a calculator. We're going to evaluate this number, okay, and see how good this approximation is to this integral. What's the exact value of this integral? 1/3. We did it last time, right? So this is going to be something like 0.32, I believe, something like this. So it's not going to be precisely the exact value, but it's going to approximate it. And if we take a higher n, we'll get a better answer. Okay? Questions? Question?
What about 1/8, 3/8, and 5/8?
Where did they come from?
Yeah.
So these are these values. Okay, these are the sampling points. For each interval, I have to take the middle point and evaluate my function at that point. So if I use different color, inside each interval, I calculated the middle of that interval. So my first interval goes from 0 to 1/4. I only have 4 intervals, this, 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 and this. For the first interval, the middle corresponds to 1/8. I have to evaluate my function at that point. The function is x squared, so the function evaluated at that point is 1/8 squared. That's the first term. Then I have to take the second interval. Its middle is given by 3/8. The function at that point is given by 3/8 squared, and so on. I add them up. More questions? Okay. So next, let's go over some properties of definite integrals. So the first property, I write down here. The integral from a to b, f of x dx. The limits of integration, a and b, can be swapped. And we actually can go from b to a. So if a is less than b, we can go this way, or we can go the other way. But the corresponding integral acquires a negative sign. Why is that? Because when we go in the positive direction, the increment, delta x, is a positive quantity. When we go back, the value decreases. So the increment is negative. Okay? So if you look at the Riemann sum, you end up multiplying by a negative value, delta x. So we have a minus sign here. Something that immediately follows from this is the following. The integral of f of x dx from a to a. What's that equal to? 0. Two reasons for this. The first reason comes from this formula. If I take them both to be a, then this is equal to minus the same thing. So this can only be 0. The other reason is that we're considering the area under a curve of an infinitely thin base. So it has to be 0, right? Okay. So then let's list a bunch of properties that will help us evaluate very many integrals and Riemann sums too. So property number 1 states the integral of a constant. And it's equal to this. So let's suppose that my function is a constant c, which can be negative or positive. Okay. So then this object on the left, it's either the area under this curve, if this is a positive constant, or it's the area above that curve with a minus sign. So it's the same thing. And this is a rectangle. So the area is equal to b minus a times c. And that's what we have here on the right-hand side. Okay? So it's very easy to evaluate a definite integral of a constant because it comes from this geometric consideration. Questions? Okay. The next one talks about the integral of a sum of two functions. So here, both f and g are functions of x. Question?
Just to make sure, I can't see, is that an equal sign in problem 1?
Here, yes.
So that only works if, oh, no, I see, never mind.
It works for both positive and negative values of c and also for c equals 0. Okay? So if I have a sum of two functions, then I can evaluate the integral separately. It's f dx plus g dx. Oh, g dx. How do I know this? This is very easy to prove. All I need to do is recall the definition. Okay. So this is the definition of the integral of f of x. So I can replace f with f plus g. Then I'll have f plus g here. So I can split this sum into two sums, one with f, the other one with g. Then I can evaluate the limits separately, the limit for the f sum plus the limit for the g sum, and that's equal to these two things. Okay? So I'm sorry, I shouldn't forget to put the limits of integration. Because what I just wrote actually has a very different meaning. That's the antiderivative. That's not what I'm talking about here. Okay, property number 3. The integral of a constant times a function is given by the same constant times the integral of the function. Proof? We go here again. If we have c times f here, then we have c times f here. C comes out of the sum. C comes out of the limit. And what we have is c times this, which is given by the integral times c. Okay, and finally, property number 4. I'm not sure why it's listed as a separate property in the book, but it's the integral of a difference between two functions. It actually follows from properties 2 and 3, but I write it down nonetheless. So the integral of a difference is the difference between the two integrals. And next we apply all these rules to calculate an example. So look at the integral from 0 to 1, 5 plus 2 x squared dx. So one way to approach it would be to do it by definition. Write down the limit of a sum of this thing, create a partition, calculate sampling points, and then do the sums and then the limit. It's very, very tedious. We're going to do the same thing by using the rules. So we notice that the integrand is the sum of two functions. So by rule number 2, I'm going to present it as the sum of two integrals. So this is rule number 2. I can evaluate them separately. Okay. Now, the first one, we have to look at rule number 1, which is a constant, right? We have 5 here. So we have 5 times 1 minus 0. And that's by rule number 1. So I dealt with this one nicely. Now this one, we have to look at rule number 3. We have a constant inside. 2 comes out. So we have 2. So this is rule number 3. So what's this equal to? I already asked you like 5 times today. 1/3, right? So we're going to use this fact to write down the answer. Okay, very easy. So if we can decompose it somehow and follow different rules, we can evaluate integrals easily. Questions? Now, property number 5. Let's suppose that I have an interval from A to B, and I look at an integral of f of x dx, and I define another point, C, which may or may not be between A and B. Actually, it could be anywhere else. Okay? Then I can rewrite this integral as the sum of the integral from A to C plus an integral from C to B. I will illustrate this with a picture. Let's suppose, for simplicity, that f is positive, and the quantity on the left has the meaning of the integral under the curve. Question?
Just to make sure I'm on the same page, you said C is between A and B?
Doesn't have to be. So in this example it is, but in general it doesn't have to be. It's just another constant. Okay? And you can prove it, of course. But here we illustrate it with an example that is more obvious. On the left, we have the area under this curve, the whole thing. Now on the right, we have two integrals, which is this area and this area. You add up the two, and you get the full thing. Right? So this is the meaning of this property. As an example, for instance, we can say that we can write this down as an integral from 0 to 1, 1 to 5. Okay. So this is an example. Okay. Question?
Can you draw an example if C is not in between A and B?
Yes. So let's consider the following geometry. A, B, C. So we have to assume, in this case, that f is actually defined for the whole interval. Okay, so if f only exists here, we cannot do this. But if C is in the domain of f, then we can potentially define C to not belong to this interval. So this is my function f. Okay, so I have an integral from A to B f dx is equal to from A to C f dx, from C to B f dx. Now, let's simplify this. So first of all, this first interval, I'm going to use this rule and flip the limits. So I get A, B, f dx is minus from C to A f dx. Now, the second integral spans the interval from C to B. Okay, so I'm going to split this one into this plus this. So instead of this integral, I'm going to write from C to A f dx plus from A to B f dx, right? Now you can see that the first and the second terms cancel out, and I get an identity. The left-hand side is equal to the right-hand side. Okay, so it's a little bit less obvious, but it also works. More questions? Okay. Finally, the last group of properties is called comparison properties. They are numbered from 6 to 8. So let's suppose that f is non-negative. Then the integral from a to b f of x dx is non-negative. This is obvious, because for non-negative f's, the integral is nothing but the area under the curve, and that's a non-negative quantity. Okay, so we already know this. Fine. Number 7. Let's suppose that we have two functions, and one of them is bigger than the other on the same, interval. Then we can compare the integral of f with the integral of g. The function is bigger, and then the integral is bigger too. Let me illustrate this with an example. Let's suppose that both functions are non-negative, okay, for simplicity. So this is the larger of the functions, f, and this is g, okay, between a and b. So the integral of f is this whole area. And the integral of g is part of it, right? So you can see that the area under the function g is smaller than the area under the function f, and that's exactly what this says. Okay, this only works if f is greater than g. If they intersect somewhere, then we cannot make this conclusion. Finally, the last property, property 8, is like this. Let's suppose that we have two numbers, m little and m capital. Which work like this. So this is my function from A to B. And there's some value m and another one, m capital, such that they enclose this function. One is always smaller than my function, and the other one is always larger for all values of x on the interval. Okay? Let's suppose I know that these two numbers exist. Then I can make an estimate of the integral of f. Okay? I know what it's bigger than and I know what it's smaller than. What are these things? So the integral of f is this area. Now look at this box here. This is completely contained inside this bigger area. And the area of this box is m times b minus a. So I can see that the integral of f cannot be smaller than this box, right? On the other hand, let's consider the big box, this one. The area of this box is given by m capital b minus a, and it completely contains the integral. So I can have this bound, the upper bound on the integral. So I will illustrate this with an example, and then I'll let you go. Okay? The example is like this. Find bounds for the integral from 0 to 1 e to the minus x squared dx. So at this stage, we have no idea what this value is. But I can write down a double inequality that defines what it is. So let's plot this function. It's some decaying function of x, okay, between 0 and 1. When x equals 0, its value is equal to 1. And when x is equal to 1, its value is e to the minus 1. Right? So for sure, I can write down the following double inequality. E to the minus 1 is always less or equal to e to the minus x squared, and it's always less or equal than 1. Right? So this function that I plotted is bounded between e to the minus 1, which is something like 1/4, and 1. So I'm going to use property 8 to evaluate the bounds for this integral. On the left, I'm going to have e to the minus 1 times 1 minus 0. And on the right, I have 1. So to conclude, I know that this integral is between 1 over e and 1. And this is much more information than I get by just looking at this, right? Thank you very much.